Welcome to aminacademy.com. In electrical engineering regarding electromagnetism, let us discuss about Ampere's work law or Ampere's circuit law. The Ampere's law is one of the important law of electromagnetism. It is finding that expression for any closed loop path. It states that the sum of the length elements times the magnetic field in the direction of the length element will be equal to the permeability times the electric current. The law states that MMF, that is magnetomotive force corresponding to EMF, that is electromotive force of electric field around a closed path, is equal to the current enclosed by the path. Mathematically, look at here, line integral, that is H integral H vector dot D S vector is equal I amperes. I amperes, where H vector is vector representing magnetic field, where magnetic field strength, magnetic field strength, and ds vector is the enclosing path, that is vector enclosing path, vector enclosing path. I is current. Ampere law is one of the useful law which relates the net magnetic field. Net magnetic field along the closed loop to the electric current which passes through the loop. It was discovered by Marie Ampere in 1826. This expression for the relation between the magnetic field and the current, relation between magnetic field and current, which produces, it is termed as the Ampere's law. The definition states that the line integral of the magnetic field around some arbitrary path will be proportional to the electric current enclosed by such path. The integral form of the law is given by line integral B ds equal mu 0 I. Concept of Ampere's law. For Ampere's law, all currents have to be steady. So currently does not change with the time. Also, only current crossing the area inside the path must be considered and will have some contribution to the magnetic field. Current should be taken with their algebraic signs. That means positive or negative regarding the path. When we use the right hand rule to determine its direction and signs, the total magnetic circulation will be zero if the magnetic field is normal to the selected path at any point. Ampere's law will also be useful while calculating the magnetic fields of current distribution with a high degree of symmetry. Application of Ampere's law. Ampere's law is having many practical applications. Its main application is the computation of the magnetic field generated by an electric current. This is also useful in electromagnets, motors, generators, transformers, etc. In many calculations, Ampere's law simplifies the process by using certain symmetry. Now, in that subdivisions we'll look further about magnetomotive force, that is MMF, around a long straight conductor. Here, look at this figure. In this figure, shows straight conductor. There is a straight conductor which is assumed to extend to infinitely in either upwards, in either direction, upward or downward. Let it carry a current I amperes. upwards, suppose the current I amperes upwards, the magnetic field consists of a circular lines of force having their plane perpendicular to the conductor and their centers at the center of the conductor. Suppose that the field strength at the point C. Suppose the field strength at point C, that is distance r meters from the center of the conductor H. Conductor is H. The field strength is H at the center. Then it means that if a unit n pole is placed at C, it will experience a force of H newtons. The direction of this force would be tangential to the circular line of force passing through C. If this unit n pole is moved once around the conductor against the force, the net work done, that is MMF, magnetomotive force A, equal force into distance. Force into distance, that is equal to current I. Therefore, I equal H into 2 pi r circular distance, 2 pi r joules, which is equal to I ampere. That is I ampere. Then therefore, or we can say H equal I over 2 pi r, which is further equal integral H vector dot ds, that is equal ampere, that's I. You can say it's ampere. This obviously, if there are n conductors, suppose the conductors are a single conductor we are using, suppose there is in center n conductors are core, then we can say H equal for n conductors for n conductors, we can use capital letter here, n conductors. Therefore, we can say H equal Ni, n times I over 2 pi r, that is ampere per meter Oersted. We can say it is Oersted. This unit is called ampere per meter is Oersted, and B equal mu0 Ni over 2 pi r, which is further equal mu0 mu r Ni over 2 pi r. This is for air. In air, Weber per meter square, Weber per meter square Tesla. In air it is the same things in medium. These are the expression for the current. Now next one, magnetic field strength for a long solenoid. Suppose here the solenoid is continuing here like a spring. In a long solenoid, the value H remains constant throughout the length L, and the volume of H outside the solenoid is negligible. Suppose a unit n pole is placed at a point A, that is inside, that is outside the solenoid, and is taken once around the complete path shown dotted. Suppose here like this, here also. Now we can say the, by definition you can say H into L joules equal ampere. Therefore, then generally you can write H into L equal Ni, and H equal to Ni by L. Then also B equal mu 0 mu R Ni over L Weber per meter square. Weber per meter square. Here this is Weber per meter square is R, it is Tesla, or the unit is Tesla. Then further B equal mu 0 mu R Ni over L Weber per meter square. It is in medium, this is in air. This, remember these formulas, it will be useful for further calculations. We have done. Please subscribe our YouTube channel.